Hello everyone, welcome to 7th week. Today we have Professor Geoffrey Hammond to talk about energy transitions and the different technologies needed to achieve it. So welcome today, and if you have any questions, please feel free to pop them in the box anytime, and we'll take questions at the end. So I'll pass it to Professor Hammond to introduce himself and also to introduce the talk.
Have we got the slides handling?
Yes.
Full screen?
Can you see it now?
Yep, that's fine. Okay. Right. Good evening. I'm sorry we're a little bit late. We had a bit of technical difficulty with the slides. As Annling said, I'm going to be talking about energy transitions and low carbon technologies. I see that on your term card, I'm listed as being at the Smith School for Enterprise and Energy. This was news to me. I would be grateful if you could ask the director if he could tell me what appointment I have there and what he's planning to pay me. That would be very helpful, because I thought I was at the University of Bath. So I'll speak as if I'm at the University of Bath. Could I have the next slide, please?
Sorry.
No problem. This is an outline of what I'm going to do. I'll say a few words about key energy challenges that are open to us at the moment. And then I want to talk about energy transitions. And we'll start by talking about world energy transitions, going back to around about the time of the Industrial Revolution and what might happen in the future. I was the principal investigator and co-leader of a large consortium of university academics, 9 of us, which looked at developing a set of transition pathways to a low carbon economy. And the focus of that consortium was on the electricity sector and including the electrification of heat and transport. So that's the main focus of the project I'm going to talk about. The specific research that we did at Bath was looking at the environmental impact of those transition pathways. And we did that in 2 ways. We looked at the environmental life cycle assessment of the pathways, and we used a technique called ecological or environmental footprint analysis. And after I've said a few words about that, I'll talk about large-scale generation and what are the clustering opportunities, how we might extract carbon from power plants, but also from industrial plants. And towards the end, I'll say a little bit about distributed generation, small-scale generation, because that formed part of one of the transition pathways we looked at. And finally, I'll have some concluding remarks. Can I have the next slide, please? So obviously, this talk is about energy, and we're interested in things like energy security. But we also have to have regard for climate change. We have to have regard for other forms of pollution, air pollution, which has environmental effects. And if we're concerned about the developing countries, we also need to have some concern about energy access. Next slide, please. I said I'd say a few words about world energy transitions. This slide shows the percentage of primary energy made up of different sorts of energy resources, going back to 1850, that's near the Industrial Revolution in the UK, and stretching out to 2050. And we can see that before the Industrial Revolution, most of the energy sources were traditional sources. These are things like wind and water power. If you were in a developing country, it might be dung, etc. After the Industrial Revolution, there was the use of coal took off. So you see a big spike in coal use. After the Second World War, warships were converted from coal-fired steam-generating warships to oil-fired warships. And you've got this start to increase in oil. Then oil started to be used widely for transport. And subsequent to that, you've got developments in natural gas, in hydro, in nuclear power, and in renewables. And this slide is made up of 2 things. It's made up of historic data, the data I've been talking about up to now, but also projections forward And these particular projections are projections used by Shell. And there are two there. You can see the proposed uptake of biofuels and then renewables in general. But they have a number of different scenarios, and you get different developments in the two scenarios. So what I'm basically saying here is if you think of your lifespan, you may think that nothing much has changed in your lifespan, even in my lifespan, in terms of what energy resources we use. But if you go back to the Industrial Revolution, we see there's been quite a dramatic change. So if there's been a dramatic change in the past, there can be a dramatic change in the future. So although we've been dependent on fossil fuels, maybe we'll be able to depend more on renewables, nuclear possibly, going forward. Could I have the next slide, please? Now, I said that I was part of a 9-university consortium, and this consortium was partly funded by E.ON, the German-owned electricity utility, and the Engineering and Physical Sciences Research Council. They funded the first stage of this work, but as you may or may not know, energy utilities have been going through a bad time financially. And the second phase of this project, where we completed the project, as it were, was funded solely by the Research Council. Now, E.ON like to talk about what they call the energy policy trilemma. And it encompasses many of those things I showed in the opening slide about the key energy challenges. So we need to reduce carbon emissions in order to reduce climate change. We need to ensure security of energy supplies, and we need to reduce their costs. E.ON would talk about this in terms of ensuring that they could sell their resources profitably. But if you were in a developing country or if you were in a poorer community, you'd be talking about making energy more affordable. Could I have the next slide, please? Now, the transitions approach or transitions theory wasn't unique to this project that we developed. It was originally instigated in the Netherlands. And so this is often referred to as the Dutch transitions approach. And it basically consists of trying to see where we are at the moment. So that's the concentric circles that say now, and where we will get to in 2050, or the Chinese would say in 2060, which is on the right-hand side of your slide. Now, in order to see how we get from the old regime to the new regime, there are a number of factors that will have implications for the transition pathway going forward. First of all, there's the landscape. This is the international factors, environmental factors, cultural factors, which affect the energy system. Then we have the regime. The regime is the regulatory regime that you might have in any given country. And then you have a number of technological niches. So what are the technological opportunities that would allow us to move from a energy system that produces a lot of carbon dioxide to one that's approaching net zero in 2050 or thereabouts? I should say that it is claimed by the Dutch researchers that this approach has been used by some of their government departments. So it has a sort of pedigree. Next slide, please. Now, unfortunately, a little bit of the bottom of the slide is being cut off of each of the slides, but I don't think it's a major problem here. We developed 3 of these so-called transition pathways. And we did this by establishing a stakeholder workshop, actually at Loughborough University. And out of that stakeholder, and this stakeholder workshop included academics, it included people from the policy environment, it included people from industry companies. And out of that stakeholder workshop, we developed 3 pathways. One which we called market rules, which is, if you like, business as usual. One which is called central coordination, where you've got greater intervention by the government. And one which we called 1,000 flowers, which comes from the Chinese idea of let 1,000 flowers spring. Subsequent to the end of the project, the CEO of an energy company described these as market rules as being the blue pathway, central coordination as being the red pathway, and Thousand Flowers as being a green pathway. I don't know whether that accurately reflects what they are. So under market rules, the expectation is that you'll have large-scale technologies, nuclear power, offshore wind, carbon-ready coal, minimum interference with the market arrangements. In contrast, under central coordination, the idea is you get greater government intervention. So you get direct government involvement in the governance of energy systems. Perhaps the argument was that they might issue tenders for tranches of low carbon generation going forward. But again, it focuses mainly on centralized energy generation. And looking back, we find that there's not an awful lot of difference between the market rules pathway and the central coordination. The major difference is in this pathway, which we called Thousand Flowers, which involved more local bottom-up diverse solutions, which involved local leadership to encourage decentralized energy generation sources in the community. Next slide, please. This slide shows what the energy generation mix in terms of gigawatts of capacity under each of these scenarios going out to 2050. And as I indicated, if you look at the top, the market rules and the central coordination look somewhat similar. It's going to be too small, I think, for you to see what the different colors mean, but they're different branches of technologies. If you look at the bottom one, the Thousand Flowers, you'll see what's distinctly different there is that you've got these this light blue line, which is renewables technology. So much greater emphasis on renewables technology. So just to go through it again, from market rules, that's business as usual, to central coordination, you get a slight drop in overall energy demand in terms of electricity. That's because you get greater intervention by government to encourage energy efficiency. And then if you move down to Thousand Flowers, you get a roughly the same total energy demand as you get for central coordination, but much more is produced by renewables. Next slide, please. Now, I just want to say something about each of the ways in which we analyze these different pathways. And the first method we used was life cycle assessment. And the important thing about life cycle assessment is that you're not just looking at the operational energy. That's the energy, for example, at the power station, sometimes referred to as stack emissions, carbon emissions from power stations. You're also interested in what goes on upstream of the power station. And if you have, for example, a gas-fired power station, you'll get quite a lot of leakages in gas from the pipeline, from the gas source to the power station. And you need to incorporate that loss of carbon dioxide to the atmosphere if you're going to get a true view of what the real emissions impact is of this any given technology or any given pathway. Next slide, please. Now, I said in my opening remarks that we need not just to worry about carbon dioxide. Clearly, carbon dioxide is the most important driver. Climate change is underpinning most of what we're doing in terms of the energy sector, but there are lots of other environmental impacts of energy technologies, particularly electricity technologies. And so here we've got a spider diagram which shows 17 different categories of impacts that different technologies might have. And the red line shows what happens under central coordination, blue line under market rules, and the green line under Thousand Flowers. Now, it's difficult, obviously, to look at all these. So in some other work we've done, which I'm not going to show you today, we've tried to get a lumped, if you like, indicator of all these pathways. But today I will just talk about carbon emissions. So if we can have the next slide, please. Here you see for each of the three pathways, MR, market rules, CC, carbon centralized coordination, and DF is thousands flowers. What happens as we go out from 2008 or thereabouts until we get to 2050? And you'll see that there's a significant fall in carbon emissions under each of these scenarios. But this is the whole system, so it's upstream effects plus stack effects. If you remove the stack effects, then you'll be going much closer to zero. And this is one of the things that we identified to policymakers that they need to think about. Policymakers tend just to think about what happens in for the operational energy and the operational emissions, the so-called stack emissions, but they actually need to take account of what happens upstream of the power station if they're going to get the full benefit and indication of what each of these pathways, each of their own scenarios is going to indicate. Next slide, please. Okay, I've said, could you go to the next slide? Okay, back, can you go back? I have a feeling that these slides are slightly out of order, but anyway, we'll go on. One of the pathways, the Thousand Flowers, had a significant amount of what we call distributed generation. About 50% of the power generation, it was assumed under Thousand Flowers by the time we got to 2050, would be from decentralized sources. So what are they? So decentralized forms of electricity and heat generation would include things like industrial scale combined heat and power plants, onshore and offshore wind farms, greater use of bioenergy plants and biofuel plants, but could also include so-called microgeneration. This is where you have embedded solar PV on your roof of your house, or a small-scale wind generator, or a small-scale CHP plant. And I think at the bottom there it will say domestic scale combined heat and power plant. Next slide, please. Now, at the present time, most of our electricity comes from central power stations, but we're now talking about moving from this centralized system to much greater use of local sources of power and local sources of heat. So at the intermediate level, you might have a wind farm and industrial CHP plant, but at the domestic level, you might have things like domestic CHP and solar panels on your roof, either solar thermal or solar photovoltaics. So it's a change in culture from a centralized system to a much more decentralized system. Next slide, please. And what this decentralized system might actually look like, these are examples of technologies that you can go out and buy now. So if you just wanted to produce electricity, you might go for micro wind turbine, that's up in the top left-hand corner, or you might go for solar photovoltaic cells, that's in the middle there at the top. Alternatively, if you're basically interested in heat, then you might go for solar thermal systems, or for heat pumps, either ground source or air source heat pumps. And if you wanted a device that gave you a combination of both, you might go for a micro combined heat and power plant, which is the one that's shown on the right-hand side. Next slide, please. Now, in this consortium of 9 universities, we had a number of researchers working on the project in both phases of the project. And it seemed to us that it would be a good idea if we gave them a project which was quite separate from the principal investigators, the academic researchers, if you like. So the task that we gave to them, and we called them collectively, we called them the engine room. We asked them to flesh out this Thousand Flowers scenario, because this Thousand Flowers scenario was the one that was most different from the situation that we have in the energy sector now. I should say that I was skeptical about this particular scenario, but it's the one that's attracted the most interest from people like the Energy Technologies Institute, a private public funded organization, and other bodies. So it turned out to be of more interest than I originally anticipated. As part of this, they elaborated what the components of this 1,000 flowers might look like. As I indicated, 50% of 2050 final electricity is going to come from distributed generation. And along with these, a number of emerging technologies, the sort of thing I've talked about in the two previous slides, you would need new infrastructure, including interconnectors to our neighbors in Europe. And you would need new financial institutions in order to regulate this distributed system. It would require regional energy strategies, and it would rely on local capacity building in city regions, in municipalities, in communities, and amongst citizens. And it would also require new ways in which we could finance this transition. Next slide, please. Now, although it would appear at first glimpse that 1,000 flowers gives you lower environmental impact, and it gives you a distributed system, it gives more control of your energy sources to the consumer, as opposed to a centralized system. But there are some downsides. And a number of our colleagues looked at the investment costs associated with each of these pathways. And here we have the investment costs in these pathways broken down into what are the implications for transport, storage, transmission, the energy generators, and so on. And we see in this particular case that the 1,000 flowers actually costs you more than does some of the other technologies. That's because 1,000 flowers is quite a bit different from conventional energy technologies, and therefore we've got to invest in new capacity all around. Next slide, please. Now, just an indication of what the centralized power systems that you might be using and increase using going into the future. In the top left-hand side, you've got a natural gas-fired power station. To its right, you've got the Flamanville nuclear power station. This is the model for the power station that's being built at Hinkley Point in Somerset, the new nuclear power station in the UK. Then on the bottom left-hand side, you've got a biomass power station, then an onshore wind farm, and then you've got a large solar power system from Italy. I should say, in relation to onshore wind farms, I live in Wiltshire, and there is a planning rule in Wiltshire that says that you can't have an onshore wind farm within a certain distance of a habited building. And it turns out that there's almost nowhere in Wiltshire that you can put up an onshore wind farm these days because of these planning constraints. So that's quite an inhibition. So most of wind power development is actually going to be offshore. Next slide, please. Now, in addition to those power stations, certainly the fossil fuel ones, we need some other way of getting rid of the carbon dioxide from the power station. And this is a hypothetical diagram produced by a research centre in Scotland, which shows, in this case, a coal or gas-fired power station. You extract, post the power station, the carbon dioxide, and you discharge it into a disused oil well or gas well in the North Sea. So this is carbon capture and storage. If we're going to keep any of the fossil fuel technologies, it's likely that they're going to have to need carbon capture and storage of one form or another. Next slide, please. Now, I mentioned in my opening slide about clustering opportunities. What do I mean by that? This is a slide we produced when we were doing some work on how you reduce carbon emissions from industrial power plants mainly, but it shows a clustering of industrial plants around the UK and fossil fuel power plants. The fossil fuel plants are the ones in green. And you can see there's a considerable cluster, for example, on the Humber, on Teesside, in Scotland, and in the Thames estuary. Now, it's thought that they would be ideal candidates for extracting the carbon dioxide, both from the power plant and from the industrial activities, and then putting them into a central capture station and then pumping them out to the North Sea. There are certain places in the UK, like in South Wales, where you have very large steelworks, where there isn't an obvious place where you could pump the carbon dioxide. So that's a disadvantage in that instance. Next slide, please. Now, in addition to using life cycle assessment, we also use this technique of environmental footprint analysis. And this is a diagrammatic sketch of what we mean. It was developed by some researchers at the University of British Columbia in Canada. And it tries to get a measure of the impact of things like biodiversity, the impact on built land, on energy land, that's the energy uses, bioproductive sea, and bioproductive land. So the slide on the left-hand side is simply diagrammatic. And the one on the right-hand side indicates the sort of component base that you might want to get. So we want to get an indication in terms of a common measure, and this measure is in global hectares, so a measure of the size, the land size, of built land, carbon emissions, embodied energy, materials and waste, transport, and water. Next slide, please. And if you look at each of those components, and you look at them in this case for different sorts of power technologies. So on this slide, we've got both large-scale technologies. So on the far left, you've got coal, but also oil, but we don't use very much nowadays, gas, nuclear. And then in the middle there, you've got biofuels. And again, this is an example that people, before we did this research, may not have realized that in the case of biofuels, obviously you're using a lot of land in order to grow the biofuels. And therefore the land footprint is much larger than even some of the fossil fuels. If anybody's worried about the column on the right-hand side, which is other thermals, those are power stations which are very little used. So there are one or two in Northern Ireland, but otherwise they're not used. So then that's not a significant effect. You'll see that the footprint for hydro, wind, and solar is very low. Next slide, please. Now, I'm just showing here a group of slides for the Thousand Flowers pathway. If you look at, excuse me. If you look at the slide on the bottom, that shows you the, I think, I can't even read these slides myself. Yeah, so the one on the bottom left-hand side is looking at the total amount of environmental footprint going forward. The interesting thing about this is if you look at the built line component, you see that's quite large. It's about a quarter of the total environmental footprint is due because of biodegradable land. And the top slide is the equivalent data in slightly different colors, but this is in terms of the footprint per gigawatt hours of energy use. Next slide, please. And the final one I want to show on this group of slides is this one, which again shows market rules on the left, central coordination in the middle, and Thousand Flowers. And again, the message here is that out in 2050, if we were to have the sort of pathways that I projected, or that the consortium projected, Thousand Flowers gives you quite a large environmental footprint. It's about, I don't know, 40% larger than those associated with fossil fuels. And this is a result we didn't expect before we started the project. So it's something that you've got to worry about. If you use a lot of biofuels, one of the downsides of biofuels is land use of one sort or another. Next slide, please. Okay, so I have two concluding slides, which are just about bring me up on time, I think. If we look at these transition pathways, the first thing we can say is that these have benefited by what some people call a whole systems approach. So we haven't just looked at the power station themselves. We've looked at what happens upstream and what happens downstream of the power system. So we look at the whole systems approach. The project overall was collaborative. It was often interdisciplinary. This consortium of 9 universities, we had about 50% were engineers. Actually, I'm a mechanical engineer, but they were mainly electrical engineers. And 50% were things like economists, economic modelers, economic historians, social policy analysts, that sort of thing. We used a combination of quantitative and qualitative analysis. The way in which we looked at these pathways enabled us to elaborate and examine the pathways, and we looked at how we might realize this socio-technical transition to a more secure, affordable, and low-carbon energy system in the future. It enabled us to identify a number of challenges and opportunities, and we think it suggested a variety of plausible ways forward. There are other ways, there are other scenarios, but this is one set of plausible scenarios. Next slide, please. And just to finish off, I thought I might just look at, because we're in the week when the government's announced its green industrial revolution, I would just look at a broad brush picture of the technologies that we might need in order to achieve the sort of industrial revolution that they want. First, in the energy sector. First of all, there are plenty of opportunities for energy efficiency and heat recovery. I've talked about combined heat and power plants. I haven't really said much about biomass CHP. If you have biomass CHP, you get what's called negative emissions. So that offsets emissions from other difficult to decarbonize sectors. And you might use industrial heat pumps. There are opportunities for fuel switching. In the past, we've moved from coal and oil to gas and electricity. In the future, we might move from them to biomass or bioenergy and potentially hydrogen in the future. I mentioned carbon capture and storage. We might also be able to utilize some of that carbon for chemical processing, for example. If you use carbon capture and storage coupled with biomass as the fuel supply, then you get these so-called negative emissions. And I mentioned that those might be ideal candidates for the development of carbon capture and storage clusters and greenhouse gas pipeline networks out into the North Sea. And finally, obviously, we want to decarbonize the electricity sector, which is what I've mainly been talking about. So facilitating low carbon electrification of heating for both buildings and processes. Last slide, please. And thank you all for listening, and thank you to our main sponsors and research consortium partners. Thank you. I'm happy to take any questions.
All right. Okay. Thank you very much. Okay. So currently we don't have any questions coming in yet. I have a few questions I would like to ask myself. So as you mentioned, there's the central planning, there's the market-based, and there's the salt and flour approach. So what combination, like what proportion of each do you think we should embrace towards a net zero future?
Yes, what I didn't say in the presentation was that these are, if you like, idealized pathways going out to the future. But we talked a lot in the consortium about how you might move from one pathway to another, or how you might, as you indicated, you might get a combination of the different pathways. I guess the likelihood is that we will not get any one of those. We'll get some combination of them. Some people would say that the Thousand Flowers pathway wasn't that radical. In other words, we only had 50% decentralized energy by 2050. And there are now people in the United States and in Europe who are talking about 100% renewables energy system. And I was once asked by a distinguished energy policy researcher from Exeter University whether this was possible. And actually, that was not an answer that I could give her directly, but I did consult the rest of the consortium, these other 9 universities. And the conclusion we came up with was that it's possible to get 100% renewables, but it will be very costly. You saw the about 40% increase in cost between market rules and Thousand Flowers. Well, if you had 100% renewables, there would be an even greater cost. So it would be expensive. And so I think we're unlikely to get 100% renewables. Oh, one other thing that I didn't say in the course of my presentation, I gave a talk on this sort of topic at a conference in Dubrovnik in Croatia. And in the Q&A session, there was a young lady there from the Wuppertal Institute in Germany. And obviously E.ON, who funded the first part of our project, comes from Germany. And I can't remember exactly how she phrased her question, but it was basically saying, how much did E.ON interfere in your project? How much did E.ON tell you what you had to do? And I had to tell her that actually E.ON didn't interfere at all in a project. They sent young industrialists along to some of the workshops that we had and gave us interesting advice. But what they were interested in was not telling us what we should do, but finding out what these different pathways would look like. And the reason why they were interested in that is they are looking at what happens in the future. E.ON and other utility companies have got to accommodate to whatever market we end up with in 2050. So they were interested in seeing what pathways we came up with, what were the challenges, what were the opportunities, and ultimately internally to E.ON, they wanted to see how they could make best use of these ideas.
Yeah, it's very interesting. So, do you think that utility companies might actually be kind of a source, like a force that we can kind of like make them help to contribute to the transition?
Yeah, I mean, I don't think that there's a feeling that some of these utility companies are are not that sympathetic to low carbon future. I haven't actually found that. Before this project started, E.ON were already talking about looking at low carbon futures, and some of the other energy utilities are as well, because they know that things are going to change. And from time to time, we've heard companies like BP. BP at one time talked about reframing itself as Beyond Petroleum rather than British Petroleum. Now that didn't go down very well with their shareholders, I have to say. So they moved away from that. But they've started again to pick up work on doing more on renewables and the like. They're still going to be quite heavily invested in fossil fuels, and many people think that fossil fuels will still be with us, possibly past 2050. The way we could live with fossil fuels, obviously, is if we got carbon capture and storage to work properly, because then we could take it out and bury it in the North Sea or other areas of the world which might be inland and therefore buried underground. So carbon capture and storage would be an important technology if we want to retain fossil fuels of one sort or another.
Okay, we just had a few questions coming in. So first one, what do you say about challenges like a large amount of mining land areas and non-recyclable waste resulting from methods such as solar?
Yeah. Well, it is a problem. I have done work, we published work on battery technologies, for example, and rare earth metals. And in both cases, you have a lot of overburden. So if you strip the land to take out the minerals, lithium, for example, then you have to do something with the overburden, the waste material. So it is a significant problem. And it's quite important that we start thinking about some of these technologies, batteries and other technologies, in terms of what people are now talking about as the circular economy, so that we try and reuse, recycle these materials going forward. There's not too much being done about recycling sophisticated battery technology materials at the moment. I hope that helps.
Okay, thank you very much. And my second question has two parts. Firstly, given the central coordination scenario achieves the greatest decarbonization of electricity generation and has a relatively low environmental footprint, would you say that that should be the favored approach?
Yeah, well, first of all, let me explain that within this 9-university consortium, we had people with quite diverse views. So, for example, there was a colleague, not one of the co-investigators, but one of the researchers. Well, perhaps I shouldn't. Well, let's say, let's say a university in the Midlands, who was very keen on hydrogen. But one of the things that I tried to emphasize to everybody is that we shouldn't have a preferred option. So the investigators, that's the academic leaders of the consortium from these 9 universities, didn't come up and say this is their preferred way. Now, as Sylvester has said, that particular scenario, that's greater government intervention, does lead under certain assumptions to greater decarbonisation and a lower environmental footprint. So we would report that, and we have reported that in various papers and stuff. But we wouldn't advocate that. And we're not an advocate of any particular scenario. We're trying to analyse what would happen under different scenarios and let other people, policymakers and so on, decide what they should do going forward. I hope that helps.
Thank you. Do you think there's like one approach that might be more effective, or like what kind of planning should, from the policy administrative perspective, is there one that'll be more beneficial or like easier to implement?
Well, I guess, I guess a policymaker might say that market rules, the existing system is easier because we know how to use that. We have all the supply and distribution technologies. We know all about it. So in a way, it's the technologies that we don't know quite so much about, say hydrogen, for example, carbon capture and storage, modular nuclear reactors. Those things are going to give us the most problem and are sometimes referred to in academic circles as disruptive technologies, not because they necessarily disrupt the community necessarily, although something like fracking might do. But they disrupt the lives of policymakers, make it more difficult for them. So I guess it depends where you sit in the policy-making framework.
That's very true. Okay, thank you. So we don't have any more questions coming in. So if you do have any questions, please feel free to pop them in the chat, either on YouTube or Facebook, and we'll take them at the end. We have about 10 minutes left. So while other people still put in their questions, I'd like to ask Professor Hammond about the biofuel you talked about, how like it has some really large environmental footprints. So do you think there's any way forward that we can substantially reduce that to make biofuel a widely effective and efficient way for energy transition?
I think there are several ways. We obviously we want to use wasteland and not land which is in competition with food crops for a start. Some of the technologies, for example, algae are a water-based biofuel, and that doesn't give us the same land impact as biofuels that you have to grow on land. You can use waste products. For example, I was involved specifically with Nottingham University in looking at how you might use timber waste, that sort of thing, in making biofuels, and it's quite complicated from the biotechnology point of view, but it clearly has a benefit from the environmental point of view. I should say that a few years ago I went on a visit to India with a number of British academics, and in India we were working alongside Indian academics funded by their Department for Biotechnology. And when they talk about algal biofuels, these biofuels that grow in water, they are not thinking about the same sort of biofuels as our biotechnology researchers are thinking about. Our biotechnology researchers are looking at sort of small microbe level algal growth. In India, they're looking at very large macro scale algal plants to grow, but that might be very good for them going forward in the future. So there are lots of ways that we could offset the findings that we had. The findings that we have do depend on growing various sorts of biofuel crops on land that might otherwise be used for, say, for growing food or whatever.
I've read about waste energy, so kind of like food waste going into becoming biofuel. Do you think that would be a possible approach here in the UK?
Yeah, I think it's a very good idea. We use a great deal of waste. We did I mentioned very briefly this idea of the circular economy. Being engineers, we like to use thermodynamic methods. I haven't really talked about them in this presentation, but we had a project which looked at what are the thermodynamic benefits of a circular economy approach. And we found that one of the largest areas was food waste. Actually, so reducing food waste is a very good idea and would be a key part in this idea of the circular economy going forward.
Yeah, I'm quite interested in that area actually. So I did a little bit of kind of like field work about food waste here, and it's quite a big problem, especially with like university kind of dining halls and this kind of systematic things.
Yeah.
So that's very interesting.
Okay, I've eaten in one or two of your dining halls.
Did you like them?
Oh yeah, that was very nice. I can't remember which colleges it was. The various research organisations often outside term time use the Oxford colleges and Cambridge colleges actually for residential workshops and so on. So I've eaten in quite a few of them over my career.
Okay. I think that's all the questions we have so far. And seeing that we're about the time to wrap this up, so I'd like to firstly thank Professor Hammond for joining us today for a very insightful and very informative talk. And also thank you to everyone that are watching us today. I know it's 7th week, you all have lots of work, it's almost the end of it. So thank you for taking the time to join us today and to learn more about energy transition and the different technologies. Remember to tune in next week at the same time, Wednesday, 5:30 p.m. We still have another event coming up. And if there's no more questions, I think that's all we have today for you. And thank you again for Professor Hammond.
Thank you.
Thank you. See you next week.